Hello everyone, good morning and welcome to the next session of our Digital V-Days. The topic of today is wrong topic. Topic of today is creepage and clearance of connectors. I'm very happy to welcome all of you and very happy that you took the time to participate in our webinar today. This is the third session of our Digital V-Days. And just for the information, there are a lot of other sessions coming. You can just also register to them as well on our homepage. Our referent today is Vamsi, Krishna, Gajula, and I'm also very happy to welcome Vamsi as well. He's working as a field application engineer at Würth Elektronik. And yeah, so just before we start with the webinar itself, I would like to point out one thing, and this is you will be muted during this webinar session. Nevertheless, you cannot ask us questions via the microphone. I think you will know that. But you have the opportunity to ask us your question with the Q&A function, and you will find that on the lower right-hand side of WebEx. We will then the presentation will be about 30 minutes long. Then afterwards, we have 10 to 15 minutes scheduled for the Q&As. And if we don't have the time to answer all your questions within this live session, we will then afterwards send you the answer via email, so you will get your answer. And also that you, if we can't answer all, or if you have any questions left after the webinar, just email us at digital-v-days@we-online.com. Also, after the webinar is over, you will get a link from us in the next day via email with the link to the presentation. I think you can also download it directly in the session now, and also to the recording of the session. You will find all that information as well on our homepage. So enough from my time, or from me saying, I wish you very good webinar, an interesting webinar, and I will hand over now to Vamsi. Have fun.
Thank you, Max. Thanks for a nice introduction to me. Okay, I'll start my presentation. Okay, so good morning, everyone. My name is Vamsi. Today we will discuss about the creepage and clearance. So before starting my presentation, I would like to start with the one example which we normally see. So what is this? So if you see this one, normally people say it is lightning. But if you ask me, it is not the lightning, it is about the clearance issue. So what exactly happening here? So if you see that during the rainy season, the clouds will be there and the earth. And during the clouds, what exactly happens is the distance between the clouds and the earth is reduced, and during the rain, because of the movement of the air and the moisture, the distance is further reduced. Because of that, there will be the breakdown voltage drop between the clouds and the earth, and the spark will be created. Because of that, lightning will be happen. The same thing is applicable to the connectors. So what exactly happens is, if we do not maintain the proper distance between the two voltage sources, the spark can be created. This is nothing but the clearance issue. So we will discuss more on this today. So what exactly? So what is the electrical insulation we require, and the most common applicable standards? Because when we talk about the clearance and the creepage, it's not only about the distance between the two voltage sources. It's about the standards which we are following, and what are the different standards available in the market. And then the creepage and the clearance tool, what are the parameters we need to consider when we are designing the selecting the component for the particular project application which we are working. And then there are other standards. Apart from that, specific standards we have, especially for the connectors, which is for a high voltage or high current application. And then we have done some product limits, like if you define the some connectors, what is exactly the value which we define in the data sheet, and what is the margin we normally keep it for the connectors. So we will talk about the what is right distance for the spark and the earth. So we would like to show one video which we design in normally. So if you talk about the best electrical insulation, what we have is the air. So if we talk about the air, the electrical insulation or dielectric withstand of the particular air normally stands for 1000 to 3000 volts per millimeters, but actually and voltage applied is 6000 volts, because in the normal environmental it is very difficult to get the pure air because of the pollution, the moisture. The distance of the air is completely reduced to the 1000. So now we have applied 6000 volts between the two voltage source, but the distance is reduced to less than 6 mm, then we can see the spark. Now we will do the same experiment by reducing the distance as well as the voltage. So now the voltage applied is 2000 volts, and now we can see the distance between two is when the distance is reduced to 2 mm, we can see the spark. So from this, what we can conclude is the more voltage you need, the more distance we require. The less the distance, then it will create the problem in this one. So now it is what exactly is we have defined in the this test. So now we will see from this presentation what is the clearance definition. It is the difference between the distance between the two different voltage source in the air. So if you correlate to the terminal block which is shown in the picture, you can see the two different voltage source are these screws and the distance which is shown in the red color. So can we increase the clearance distance for the connector? If you ask me, yes, we can increase the clearance distance by applying the plastic groove between the two voltage source, but you have to make sure that you have to use the perfect and correct insulating material. So what could be the correct insulating material for the particular product? So for that also we have done one small test in our lab. So what is the test? I'll just show you that what exactly we did. Initially we took one insulating material, normally it is called the PA66, and whose electrical insulation material, dielectric withstand material strength obviously is around 70,000 volts, as is shown in the picture, 70,000 volts, and the voltage applied is around 5,000 volts. And we have done the testing, like you can see the two different volts, and we have applied the plastic material which is PS66 and applied volt. If you see properly, the moment we are removing the plastic, and you can see the spark has been created and is a carbon has accumulated. So lightning around 5,000 volts and the applied volt is 60 millivolts, the plastic material after the test. Now we will do the same test by using the another material which is the paper, whose dielectric strength of is 1600 volts per meter and applied voltage is 500 volts. So now if you see that when we applied, even though we are not removing the material between the two voltage source, we have seen the spark here. So what exactly from this test we can say that, so if you do not use the proper insulating material between the two voltage source, then it will create also spark on that one. So it is obviously you have to select the right material for the connectors which you are talking about this one. So from this test, it is very clear that what is the clearance. Now we have seen it is the clearance between the two. Clearance is the distance between the two voltage source in the air. So apart from the clearance, so we have there is another parameters we need to consider. So for that, what we did is we took one assembled connector like USB like C, and we applied the voltage. If you see this one, you can see some sparks across the connector basically. So what we did is then we taken the connector and disassemble the connector, and when we observed that there is a plastic carbon has been found between the two pins. So what exactly happens exactly? So the current is not only the current has slipped between the two pins on surface of the material. So it has creeped the current, and the spark has been created. So that is what exactly we call as a creepage. So it is very important. So from these things, what is exactly the creepage and the clearance? So current, if you talk about this one, the current will take a very shortest part that could be through air, which is the clearance, or surface of the material, which is the creepage. So if you see in this connector, the red line which we are showing is the clearance, and the blue line which we are showing is the creepage. So again, increase the creepage and the clearance. Yes, it is possible. You can see the red line, again the clearance, and the blue line what we are showing is the creepage by this one. And you have to remember few points here. So creepage clearance can be equal or cannot be equal. It depends upon the application to application. In some applications, the creepage distance and the clearance distance will be equal. And by increasing the pitch, you cannot increase the creepage and the clearance. It is very, very important thing you need to, because it depends upon the size of the insulator of the connector. So then what is the indication? How do you get the idea of the creepage and the clearance? It is all the manufacturers will be mentioning the dielectric withstand voltage or working voltage in the data sheet, which is the indication of the creepage and the clearance distance. So this is about the basic concept of the creepage and the clearance issue. So now we will talk about the common applicable standards. So if you see in the market, so when you talk about the any product which is this one, there are few standards which is internationally applicable, and there are some standards depending upon the country to country you apply. So as a design engineer, the first question comes is which standards you need to apply for your design. So that is the one questions we ask. So to make it simple, there are some standards available in the market. A few as CUL and the CULS, which is the standard from across the US applications, and then we have IEC and the VDE. This is again the European standards for the products wise. And if you talk about another standard is IPC, which is normally suitable for the PCB design applications. So when you talk about the connectors, the most common standard connectors when you talk about in the market talk about is the UL standard. So what exactly the UL? If you talk about the Würth Electronics, all the components which we are coming with the UL standard components. And there is another standard called IEC, which is more or less equal to the UL standard only. And if you talk about another standard, ANSI, which is a Chinese standard, which is also mostly defined from the UL standard only. So when you talk about Würth Electronics, all the components which we are defined is a UL certified. And if it is in the data sheet, we have mentioned the certification number, which is defined as per the UL standard 1977. This is a standard which we normally follow to derive the UL certification in the data sheet. So which is a very basic standard which terms of the security wise or divine, but this will not completely define proper support when you get the creepage and the clearance. That's the reason we also follow different standards which also define some security standards for the UL certification or the creepage and the clearance. So that's the reason we follow different standards like VDD and UL standards also. So this is about some basic standards which we follow, and the parameters which we need to calculate for the what you call the creepage and the clearance. There are 6 parameters which we need to calculate when you are selecting about the working about the creepage and the clearance. The first is pollution degree, which is much important to the equal for the clearance as well as the creepage, and the attitude only for the clearance, and then the insulator CTH stands for the capacitive tracking index, which is mostly applicable to for the creepage. And then we have the over voltage category, which is also important to the clearance. And then we have an impulse withstand. This is also only for the clearance. And then the last point you need to consider is the working voltage, which is applicable to the both clearance as well as the creepage. So we will see each point differently what exactly stands. The first thing is if you talk about the pollution degree. So we have the degree, we have 4 different degree, like 1, 2, 3, 4. And if you see another is the non-conductive pollution, which is the possible, when you talk about is the possible, and the pollution degree 2 means S, and next 3 and 4 is also S. And another point is the conductive pollution due to condensation. So what exactly it is? The condensation is exactly opposite to the vaporization. So during the vaporization, what exactly happens is the water evaporates and becomes the air. But in condensation, because of the moisture, the water will be created. So that is what exactly called as the condensation. And then we have is the rain and snow, and the application and examples. So pollution degree 1 is normally applicable to the sealed components, white roofs, and the pollution degree now 2 is normally suitable for the laboratories, and the 3 is for industrial farming, and the 4 is the outdoor application. So to understand better way, I have some examples with me. So when you talk about the pollution degree, normally if you are working for the designing the power supplies for the computer, mobile phones or the laptops, that all comes from the pollution degree 1. So how do you define in the pollution degree 1 means in the pollution degree 1, you have a ambient temperature which is controlled one. So if you're talking that it's a closed room where the temperature will be around 20 to 22 degrees only. So there you'll not get any pollution, condensations or kind of pollution for the because of rain or not be exposed. And when it comes to the pollution degree 2, This is normally components which you work in the office or I can say labs. What exactly happens is during the normal office hours, you have when AC air condition is on, so you will get the proper controlled environment. So when you switch off the ACs during after office hours, because of the heat, the moisture will be created. From the moisture again, water will be created. So this is temporarily. Again, when it comes tomorrow morning and when you switch on the all the AC, air condition and labs, again the temperature will be controlled. So here the condensation will be the temporary. So this all components comes to the pollution degree 2 lab equipment. And the pollution degree 3 comes is the workshops, where you can normally generators or in power supplies which go for the workshop level. So that all components come into the pollution degree 3. And the pollution degree 4, normally the components which is placed in the outdoor applications, example like EV charging unit, electric vehicle connector, so all which is exposed to the rain, lightning and all these things. So these are the 4 different, depending upon the applications, the pollution degree has been defined. So next topic which we need to consider is the altitude. So altitude, as we know that when you go, if there is an increase of altitude, the air pressure will come down. So normally this is we experience when we visit, when we trek, when we go to the mountains, the air pressure will be very less. So it is very difficult to take the breath. The same thing is applicable to here also. So if you talk about, if you take a connector and try to do the test for the breakdown voltage, the air pressure will be very high at the sea level. So air, as we have seen in the preview, in the beginning of slide, air acts as a very good insulator here. So if you do the test connector for the breakdown voltage at the sea level by not considering the moisture, because it is a dry environmental, the connector has a very good withstanding voltage capability. So when you talk about again, same connector, if you do the test at the mountains where the air pressure is very less compared to the sea level, the breakdown voltage of the connectors will be little bit reduced because the air is very less. So again, the what is all the breakdown voltage of the connectors is little bit reduced. And if you do the same test at the space, again the air pressure is almost near, I don't say the miss, and there the connector breakdown voltage is much lower than the compared to the sea level. But when you talk about the space level, you have a limitations. What is that exact limitation? So we will see in the next slide. If you see the graph, so if you see the x-axis, which is the pressure length, and like we talked about the breakdown voltage. So as we seen, the if you are increasing the altitude, the breakdown voltage keep on doing because the air pressure is reduced, and as we know that air act as a good insulator. So but over the period of time, you can see this one, once it reaches a certain level, then the breakdown voltages keep on increasing. What exactly happens is, if you see a completely space, there the no vacuum will not be there, and if you do not have air, then how does the current will pass through the molecules? So that has a limitations, but this is this point you need to consider for the rare applications if you are working for the space and all the things. Other than that, this point is not regularly if you're working for the industrial, automotive applications and etc. This is about the attitude. And other parameters what you need to consider, point is for the creepage and the clearance is the CTA, that is the comparative tracking. This is called CTA, is a comparative tracking index. What exactly we do test is, here we will see the electricity holding the capability of the plastic which can insulating material which can hold the electricity by not allowing the skidding to other part. So if you see this test, what exactly we are doing is, we are the white material what here seeing is the insulating material, and we have applied the 2 voltage electrical source between with a certain distance, and there is a liquid, contaminated liquid, it will be falling on the 2 electric sources at the 30 seconds. This is all defined as per the IEC standards, and every time when the drop falls on the 2 electric volts, there is a discharge of the current. So over the period of time, if you see this one, there will be once the distance between the 2 voltage source is reduced, and then you can see the spark has been applied. You can see that block you can see that there is a fire has been occurred because of the breakdown of the voltage, this one. So this is very good test to define the holding capacity of the current of the plastics. So based on this test, we define the materials into three categories. The plastic which can hold up to 600 volts is defined into material group 1, and the plastic which can hold up to 400 volts defined into the material group 2. And then we have 175 volts and 100 volts, which is the material group 3A and 3B. So based on this, we have seen that the plastic materials like PA, PTFE, PBT, PC, and LCP. So PA is a very good, has a CTI value which is around 600, which comes the material group 1, and the PTFE are also very good material. It comes again the 1, and rest we see the PBT and the PC, LCP comes respective 2, 3A, and 3B. So if you observe one thing, when you talk about the plastic materials, LCP is a very good material with respect to operating temperature, but when it comes to the CTA value, LCP has the least value, least material. This is a one reason. If you talk about terminal blocks, most of the, I can say 95% of the terminal blocks housings has been used as insulating material from the PA. That is PA 66, we can say precisely PA 66 or PA 60 materials has been used in this one. So this is about the CTI value. And another point which we need to consider is the overvoltage category. So if you see the overvolt category, this is also we have defined into the 4 different categories depending upon the application: category 4, 3, 2, and 1. So category 4 comes the component, the products which are directly exposed to the lightning or the rain. It's like transformers and this one. So there is no protection for the products. And then we have a category 3 where the components comes from the category 4 to the electrical circuit boards or the wall mounted circuit boards like elevators or the motors, generators, all comes to the category 3. And then we have a category 2, which is normally comes from the products which are from the electrical sockets. This one like washing machine or refrigerators or the electrical lamp, water purifier, all this comes to the category 2. And the category 3, category 1 normally comes with the special what you call protection. Like if you talk about the mobile chargers or electrical laptop chargers which has a special category 1, this all components comes to the category 1. So when it comes to the Würth electronics, we have a component which can support to the category 3, very few, and mostly category 2 and category 1 where we will support to the components. And then one more thing which you like to discuss is the, as a design engineer, if you know your application, you can reduce your working voltage. So this is a table which we directly taken from the standards. And if you see this one rated voltage category, and for example, if you are working, let's say designing the power supply for the, again, I'm taking for the mobile or the laptop, so whose normally comes with the 300 volts, and based on that you can categorize which comes. Like if it comes to the category 1, the voltage capacity it can withstand up to this 1 kV. So if you are working for any other application, if you know the operating voltage, based on that you can define what is the over voltage category and the values. This is values directly taken from the standards, not from, it's defined from the Würth electronics. And another point we need to consider is impulse withstand voltage. So impulse withstand voltage, we know that what is impulse withstand voltage. It is highest voltage is applied at 1.2 microseconds and the voltage is reduced for the 50 microseconds. This is about the impulse. And when you talk about the dielectric, is the maximum voltage, current or voltage can an insulator material can withstand with the prescribed given time. So here in the data sheets, if you talk about any products, the dielectric voltage withstand is given, but the peak value is not defined. So if you want to get the peak values, is obviously you have to multiply the value with the √2, then you will get the peak values. Then if you observe that one, the dielectric withstand value is much higher than the impulse voltage. That is the one reason in the data sheet we will not be mentioning the dielectric withstand peak voltage, only the VDC voltage is mentioned. If you talk about the strength wise, how does you can compare with the impulse as a dielectric voltage? Impulse voltage, you can take one page and you try to pull it in a horizontal way. You feel that it will not tear very easily. But whereas if you take it the book and try to pull it in horizontally, it will take more strength to break it. So you can make it the dielectric withstand. So this is the one reason we normally mention the dielectric withstand in the data sheet. Even customers also would like more than the impulse voltage. So now impulse voltage, this is the data sheet of any terminal block. If you see this for electrical parameters, we have given the working voltage is as per the VDE is 450 volts VAC and the working withstanding voltage is 200 volts. So we need to get the highest peak values. Just we already multiplied with the root square, we got 3.5 kilowatts. Again, when we compare with the table, which we taken from the standards. So as per the working voltage 450, which is near to the 600, as per standard, it has to go for the 2.5 kilowatts. But in Würth Electronics, whatever the product we define, we have some margin. So we define it to 3.5 kilowatts. It is much higher than the what exactly as per the standards. And then the last parameters which we need to consider is the homogeneous field and inhomogeneous field. So what exactly the homogeneous field? So homogeneous field, the product looks like evenly, right? Where the there is a proper electrical flow will be there, so there will not be any electrical condensation will be happening. When you talk about the inhomogeneous field, you have a sharp edges like this. So at the edges, you will find the electrical condensation. So if you talk about the passive components, most of the 90% components, 90 to 95% components are comes to the inhomogeneous field because they have a sharp edges. The only component which we can categorize into the homogeneous field is the capacitors. So you can see the capacitors where you have a low electrical condensation happens, but rest of the like as you can see in the picture, switches or any connectors which has a sharp edges comes to the inhomogeneous field. So now we have seen all the parameters which is required to calculate the required to consider the clearance. Now we will see the table. So if you see the table, there are some areas which we have not shown clearly because of the legal aspects we are not able to show, because these standards you need to buy. So when we buy, we cannot display the in publicly. But here we are showing what exactly required for the presentation. So if you see in the table, the minimum clearance attitude is 2000 meters above sea level, and we have two columns, case A, case B, inhomogeneous field and homogeneous field, and we have defined the pollution degree, different this one. So now again we consider this table, the previously terminal blocks we consider, it is operating voltage of VDC 600 volts. So this is what exactly is 2.5 is required. So you can see the 2.5 required voltage, and all this one pollution degree, if consider as that 2, then you required what you call the minimum voltage is distance is 1.5 clearance is required actually. So now we talk about the creepage. Again, in the creepage materials, we have defined the depending upon the material group, which we have seen as per the CTI value. So now we have considered the data sheet. So this is one of the terminal block data sheet. We can see the working voltage, which is given is 250 volts. Again, the insulating material is PA66. So we know that PA66 material comes in the material group 1 with the pollution degree 2. Now we can consider this pollution degree 2. This is the material group. Now we will see the working voltage is 250. So 250 working voltage, now we need the creepage values of 1.25. So this is how we need to calculate the creepage values one of the way here. So now we talk about the other standards, other than standards, what exactly we have in the market. So when you talk about the other standards, we have terminal blocks, which is normally stands for the UL 1059. As I told you in the my previous slide, the basic standards is UL standard 1977, which is a very basic standards, which is not sometimes will not fulfill the requirement of the market. So we will have to consider some of the standards like UL 1059, which is normally defined for the terminal blocks. So what exactly this standard defines? In this standard, if you see, again, we have 4 different categories as per the over voltage category. Then you can see that for the first standard service for the dead switches board applications, and then second category stands for the commercial applications, then the industrial general, and the industrial with the limited rating, and the terminal blocks above 600 volts. So again, you have see the through here minimum spacing of as per the UL 1059, through here clearance and the over surface and the creepage values. So if you talk about the data sheet of any terminal blocks, we have given the working voltage 300 volts as per the UL standard if you are working for the US market, and working voltage of VDE if you are working for the Europe applications. So based on that, you can calculate, it comes this range. If you're talking about the 300 volts, you can go for the creepage is to 2.4 and the clearance is 2.4. But if you talk about the more than 300, then you have to go for the creepage and clearance. So now we can see here, so as I told you in the beginning, the creepage and the clearance values can be equal or cannot be. If you talk about this one here, the creepage and clearance both are equal, but when you go for the higher applications, both are different. So this is what exactly I would like to emphasize this point here. And now we talk about till now we discuss about the component side. Now we'll talk about the PCB side. So when we talk about the PCBs, we follow the standard IPC 32221. So here also we have defined into the two different categories. One is the bare PC printed board, another one is assembly printed board. So bare PCB printed board defines the spacing required on the PCB. So suppose if you do not have a if you mating connector, like means if you have a connector which has only directly go and assembles the PCBs. If you talk about the Würth electronics, we have called connectors called skid connector, which does not have a mating part, a female part, which directly go on sits on the PCBs. So there we have spacing like B1, B2, B3. So uncoated one, sea level above 3004. This is the values we have defined. And when you talk about the assembly, the connectors, which is the products which are assembly on the PCBs, again we have defined the standards, which is the creepage and the clearance values. If you see this one, the permanent coating, uncoated, and permanent coating, any evaluations, the values will be different. So you need to consider based depending upon the which product you are designing, and consider these values and design the PCBs. So what should we remind now? So choose carefully standards. When you're talking about the creepage and the clearance, it's always depending upon the applications, like which standards you are following. IEC, UL for the products, IPC 2221 for the PCBs. And second thing is we like to discuss about the some tricks and the advices. What exactly design tips we can do it if you're working about this one. Is it possible? The first thing is how to solve the creepage and clearance issues. So as told in the beginning, we can increase the creepage and the clearance values, but what is the distance we need to calculate? It's very important when you are increasing the creepage and the clearance. What is the distance, maximum distance or minimum distance we need to follow? This is again defined as per the, you can make the designs like this on the PCBs, but make sure that you always follow the standards. This is also standards, we take it from the IEC standards. If you're working for the pollution degree 1, you need to go minimum is 0.25. If it's working for the pollution degree 2, it is 1 mm, and the 3 means 1.5, 4 means 2.5 mm actually. So beyond that we cannot go, below that we cannot go, because if we go over is again the standards will be deviate the problem. And how to increase the pollution degree? So if you're working for the pollution degree 1, and the same countries, if you want to decrease the pollution degree 2, is it possible? Yes, it is possible, but you need to compromise something. What exactly? So if you talk about here, so if you are working for the pollution degree operating voltage 320 and the material group 1, and working for the pollution degree 2, then this is the values. And the same countries you can go for the pollution degree 3, but we have a material group is 1.60. And the same thing when you go for 3, the material group is 1.60, which is a clearance distance, but you are reducing the operating voltage, that is 63 volts. So we can increase the pollution degree at one time, but the same other side you have to reduce your operating voltage. But you can increase the pollution degree by just adjusting the operating voltage. Then please respect the always respect the data strip length for the terminal blocks, whatever we have defined in the data sheet. So if you not respect data sheet, what exactly going to happen? So this is the data strip length. If you do the properly, then you can see the creepage value is properly created here. So this one, if you are doing if you are not following the strip length as per the defined in the data sheet, then you are reducing the creepage length here. So what exactly happens because of this one? So if we define, if you go for as per the instructions given for the crimping, so it can support up to 630 volts. If you are not following the proper crimping and you are creating, so you are using the 50% of the clearance value, creepage and clearance, and directly the connector capability, that means you are degrading the connector's capability of you have to reducing the operating voltage. This is what exactly happens with if you don't respect the strip lengths. So the last topic point which I would like to discuss is the product limits. So even though we defined the operating voltage we have defined, so when it comes to the Würth electronics, we always keep some margin here. So one of the tests what we have given is when you talk about the USB connector, so we have as per the data sheet, the breakdown voltage is 500 volts minimum, but really we have done, it can withstand up to 1000 volts. You can see that after 1000 volts, we found the carbon has been accumulated between the two pins. And when you talk about the RJ45, so we can see something exactly after applying, you can see the some sparks exactly happening here. So when we done the testing, so as per the data sheet, it can withstand up to 1000 volts per 1000 volts per millimeter, but actually it is went up to 1700 volts. So you can see the how much margin we are keeping for our connectors. And if you look at into the overall product length, what exactly we have, we talk about the we have a mini module, box headers, switches, and USB. So working voltage, we have defined 100 volts, but dielectric portion which but it can break down up to 1800. So you can see the huge, for every product, we have a huge gap, what values we have defined in the data sheet. Actually, it is going to happen in this. So this is about the practicality I'm talking about with the electronics. So what should we remain? I mean, this is, we have discussed about the creepage, clearance, and the standards before closing the presentation. So I would like to just rewind what exactly we have discussed. So clearance, it is the shortest distance in the air between the two voltage source we have shown here. And the creepage, it is the shortest distance over the surface of the connectors. So this is one important thing. And what to remain? Clearance prevents over voltage coming from the storm or lightning or the internal system. The creepage prevents from the electric call within the time. So when you talk about the what are the parameters we did, we have discussed different parameters like pollution degree, which is very important. We have 1, 2, 3, 4, and then the altitude. So as the altitude increases, the breakdown voltage of connectors will be reduced. And next point is the CTA, that is the capacitive tracking index. It is the value which states the electrical plastic capability of holding the current. And then over voltage protections, we have different over voltage protections, 4 and 3, 2, 1. So Würth mainly concentrate on the overall capability of category 3, 2, and 1, and the working voltage is also very important. So I would like to do this one, product applications, applicable the standards. Define your application parameters. It's not about that what exactly we say. It is about the design engineers who has to design the application based on the application which you are working. And the most importantly, use the standard tables, define the creepage and the clearance. So this is you, when you are working for any applications, please follow the tables which is already defined by some UL or IEC standards, and choose your products based on the applications, because it is very if you select the correct product component for your product, you can reduce the space on the PCB as well as the price on the price also. And most importantly, you can design the PCB as per the product which you are selecting, which is very important. Next one. And standards, most common usually is IEC, UL, and IPC. I'm just repeating again. So both product have a big voltage security margin for the breakdown when you talk about the Würth. So breakdown brings low distraction for the Würth product ends, because we work on the categories like 3. If you talk about the voltage category, it comes 3, 4, 3, 2, 1, and as well as the pollution degree is also like. So that's the reason when you talk about the PCB and using the components, we have a first thing is we have a huge security margin, and second thing, it brings the low destruction. It will not burn any component because of the creepage and clearance issues. And using the Würth component, it will not affect the entire product, like or damaging the entire products. We have not seen anything like that. Okay, so with this, I conclude my presentation. If you have, I think I'm on the time. I think if you have any questions, please ask me.
Okay, so thank you very much at first, Vamsi, for your time and yeah, for the presentation, for the interesting presentation. Yeah, as you already said, now we would like to turn our attention to your questions. And yeah, we can see that there are already some questions. So yeah, let's keep in time and start with the first one. Is the creepage and clearance distance the same for all connectors, Vamsi?
No, exactly. It depends. As I told you in this previous slides, creepage and clearance can be equal or cannot be equal, depending upon the size of the insulator. If you're talking about the 2.54 and if you talk about the 4.20, so though you can see the what you call the insulation material, the size of the mechanical size of the connectors will be different. So based on that, the creepage and the clearance values will differ. And the second thing is the pollution degrees also. So as I told you again, it can be or cannot be equal.
Okay, thank you very much for the answer. So then we have a look at the next question. So yeah, Vamsi, by increasing the pitch of connector, can we also increase the creepage and the clearance distance?
No, we cannot increase that one. It is again depends upon the parameters which you are working and the application which you are working and the standards and the tables what we have, which I've explained in the presentation. So you need to consider all this, then only we can calculate the creepage and the clearance values. But by increasing the pitch, you cannot increase the creepage clearance distance.
Okay, thank you very much. Then we will go on with the last question. Just time-wise, we have to keep in schedule. Yeah, as we have a lot of other sessions coming in our digital V-Days. But now, last question. How and where can we get creepage and clearance distance of connectors?
It's not, we will not get, it is the indication what we give in the data sheet, like working voltage. That is where you can give the indication. Based on that, you can again get the tables, what I have explained right now, and then the application which you are working. Based on that, we can get the calculate the creepage and the clearance values.
Okay, thank you very much. So I see there are some more questions coming in. We will answer them via email afterwards. So you will get your answer, and also you can just write us an email at our email addresses, which you can see at the slide at the moment, digital-v-days@we-online.com, or write directly to Vamsi. So then, thank you very much for your attention. Thank you, Vamsi, for your time today and your presentation.
Thank you. Thank you for your time also.
So then, I hope you enjoyed our webinar, and maybe we can see you at our next Digital V-Day session again. And from me, have a good day. Bye.